For lesson 1.3, we'll be looking at distance as a function with the goal of writing and graphing linear distance equation. The importance here is that distance and velocity are linked through rate of change. So in order to be able to make these equations, you want to be able to understand distance as a math language. There's a few different words that get used a lot that kind of give you the keys and understanding for how to create our equations here. The big thing is noting the difference between movement that is away from some position or back towards a position. Generally, the way that we regard it is if you are moving away from a starting point or a point in general, that's positive movement, meaning the graph is going to increase as it moves to the right. However, if you're going back towards something, that constitutes negative movement, meaning that the graph will decrease as it moves to the right. This is obviously something that's going to have an impact on the slope of the equation. So here's a few examples of that. For one, we've got a car that is leaving home and driving at 60 miles an hour for 2 hours. So we have a 60 miles per hour here, which again is a velocity. So it's pretty safe to say that this is our slope. And if we are leaving home and driving probably away from it, it's safe to assume this is probably a positive 60 right here. Therefore, I would most likely write an equation d equals 60t. Now, I'm not using x and y in this scenario. I could, and it would give me the exact same graph. It's not really a big deal, but I'm trying to stay consistent with the real life stuff that we're looking at here. So instead of x and y, I'm going to use t for time and d for distance. Our next thing here, we have a person returning home from the store. It takes them 45 minutes to go 30 miles. This one's a little tricky for coming up the slope because we are going to have to interpret the 45 minutes a certain way, especially considering we were told that they traveled 30 miles. Normally, we record our velocities in miles per hour, so it would be good to think about how this 45 minutes works with a little bit of unit conversion here. If you think about the total 60 minutes that it takes for an hour to go by, 45 out of 60 of those minutes would then be 3/4 of an hour. So if we wanted to figure out what our actual velocity here is, we would want to take 30 and divide it by 3/4 of an hour. Remember that you can divide by a fraction by simply flipping it over and multiplying instead. So in this case, we could think of this as 30 times 4/3, which is 40. So this is going to be our slope. We're moving at 40 miles per hour. And assuming we returned all the way home from the store and this 30 miles is the total distance, this is also going to be our y-intercept. So d is going to equal negative 40t because we're returning home plus 30. This will make it so when we plug 3/4 rather for 3/4 of an hour, we will get 0, which is the distance from home. In our third example, we have somebody standing 10 meters from their home and not moving. I don't think the fact that this is in meters is actually going to matter because the really important thing here is that they are not moving. So they're 10 meters away from their home, which we could regard as positive distance. But we are not going to attach a t value because having a time value would cause the person's position to change as you put in different t values. We're also going to practice graphing a few distance graphs. They're just basic linear graphs here, so I've written down the regular instructions that you usually get for making a linear equation. Start by finding any point on the line. Usually this will be a y-intercept, but occasionally you might be given something partway through. Then you want to use the pattern of the slope to move to the next point and draw a line through those 2 points. You only need 2 points for a linear line, so this is usually enough. But you can also optionally make a third or even more points in the opposite or same direction from your second point if you want it to be more exact. We're going to actually start with these bottom 2 equations to test this idea here. The bottom 2 equations are actually both written in point slope form. So instead of starting out with the intercept, I'm going to have to start out with the point that the equation gives me. For my first graph, I have a t minus 1, and remember that the point slope formula already has a minus in it, meaning that the point I get here is 1, and this part has a plus, so we want to keep it as is for -4. So I'm going to move over to 1 and down to -4. And that's my first point on the line. The slope of 2 right here means that I'm going to be moving up 2 and over 1 to get to my next point. So up 2 from -4 would be -2, and to the right one would be right here, 2, -. These are enough points to establish a line, so I can just draw a line through these, and I will be set. Over here, we have the same situation. We want to take the opposite of whatever we see in here. So our first x value is going to be -2, and our y value is going to be -1. So we'll start with that point. We've got -2, -1 right here. And then this slope says we want to go up 1 and over 2. So up 1 would be up to 0, and over 2 would all be over to 0. So we've got our -2, -1, and our 0, 0, and we can connect these to make our line. I wanted to rewind to these last two because they're a little bit different. You'll notice that the graph on the left doesn't have any numbers in it, just d equals t, and the graph to the right doesn't even have a t value. As we talked about before, if you don't have any t value in your graph, then your graph is just going to be a constant equation with a horizontal line drawn at that y value. So for our d equals 1 right here, we can just draw a line from y equals 1 all the way across. And that would be our constant equation for this one. Over here, this t, even though it doesn't have any numbers next to it, does secretly have a 1 sitting in front of it, meaning that this is a graph that starts at 0, 0 and is going up 1 over 1, or as we call it, the identity function, because every value of x that you get is exactly the same value of y. So this is a graph that just starts perfectly in the corner and moves perfectly over to the other corner, crossing through the origin. It's important to be able to make the linear identity graph. A lot of people mess up on this because they want it to be overly complicated. So that's some graphing examples. Let's head over to Desmos and see what it says. So initially we have the same instructions here for creating a distance equation, right? Find the velocity of the equation and at least one point within the context of the problem. Moving away is positive, moving back towards is negative. The same information there. Down here, of course, the nicest thing about Desmos is a graphing calculator, so doing what we're doing here is exactly what it's meant to do. I have an example equation set up, d equals 2t minus 1. I can toggle this on and off to see what it looks like, and obviously change the numbers in front of t and behind it to get all the different graphs. If I wanted to transfer this to paper, I could always click on the graph and drag around to find a couple of points that I maybe want to trace through. I guess these look good. So that's probably the easiest way that we could transfer this onto a paper. That is it. For the next one, we're going to be looking at piecewise functions. Thanks so much. See you soon.